right. We can keep going. We saw a little bit how to do numerical integration. Very basic way of doing numerical integration. So right now we have a program that does numerical integration. One thing that isn't particularly great is that nowhere in this program is there some piece of code that really encapsulates the idea of integration. It's here and there in the code, and even though once you get a little used to these things, it's pretty clear what's going on and how you would extract it. Maybe you're not all that familiar with writing a code. It's not the assumption I'm going to make. So we need a way to extract from this program a subroutine or a function that handles integration. So we'll just do a very simple example of that. So I'm always not sure about the syntax of these things, but okay, I think that's what it is. So let's write a integration function. Let's clean up the comments. Okay, so I'm going to return a double precision number. Integrate has to take A, B, so A is a double 2. Has to take for now, we won't pass in the number of okay, let's pass that, even though we might have to change that later. And then double pointer to function. constantly just copy pasting. So okay, so at the end we return integral. Right, and so how would we call that? Oh, did we forget the H? The way it's called is you set up all of these things, basic things, and integrate, pass A, B, N, and then you pass ampersand, which means the address of func. And that should give you the same thing as before. Let's see if it works. For some reason it's better than before. Okay. Not even sure why, but oh, I know why. It's because 2.0 instead of 2. Maybe it has. Certain languages can figure out what you mean when you write just 2. It knows that 2 can be either an integer or a floating point number, and it decides which based on the context. Many modern languages have that feature. C does not, and so you gotta be aware of that. So you see, we actually got pretty good performance in terms of the number of steps. So remember, we're doing 10 sub-intervals. Doing 10 sub-intervals, and we're getting a precision. You see the difference between the actual integral and the integral we computed. If you multiply it by 1,000, it's 0.000 blah, blah, blah. So at least how many zeros are there? There are 5 or so 6, maybe 9 or 8 or 9 zeros total. So it's pretty good, but then again, the interval we started with was pretty small, right? We're integrating from 1 to 1.01, so it's, and we take 10 steps, which means the subintervals are 1,000th. That's the size of the intervals we're using. Also notice how much of a change in precision we get simply by how do I say this? If you compare this integration method with the previous one, which instead of assuming that the function is linear, it assumes it's a constant over a small interval, you really get a much worse performance in terms of accuracy. And you can say, well, of course, you know, that's obvious because functions are never constants, but linear approximations are pretty good in comparison. Well, while that is true, the actual algorithm is really not doing something much different. You know, in total, it's going to look at one more point. So it's going to look at 11 points instead of 10 points, and it's basically going to